Okay, so new definition. Let the set X together with some metric D be a metric space. Let the number epsilon be a positive number. And let the point X be in the set X. Then the set, which we denote B sub D of X epsilon, is the set of all elements Y in the set X, such that the distance from X to Y is less than epsilon. And this set is called the epsilon ball, centered at the point X with radius epsilon. Alright, so now we're going to prove a lemma. Once again, let X with some metric D be a metric space. And suppose that the point Y is in the epsilon ball centered at X with radius epsilon. Then there exists an epsilon ball centered at Y with radius delta that is a subset of the epsilon ball centered at X with radius epsilon. Alright, so prove this theorem, or this lemma. Let the point Y be in the epsilon ball centered at X with radius epsilon. Then the distance from X to Y in the metric D is less than epsilon. And so if we define the number delta to be epsilon minus this distance, the distance from X to Y, then this is a positive number. And so the set B sub D Y delta is an epsilon ball centered at Y with radius delta. So the existence part we have just demonstrated. So now suppose that the point Z is in the epsilon ball centered at Y with radius delta. Then the distance from Y to Z in the metric D is less than delta, which is equal to epsilon minus the distance from X to Y in the metric D. And so the distance from Y to Z plus the distance from X to Y is less than epsilon. And as D is a metric, we have that the distance from X to Z is less than or equal to the sum of the distance from X to Y and the distance from Y to Z, which is less than epsilon. So as the distance from X to Z is less than epsilon, we have that the point Z is in the epsilon ball centered at X with radius epsilon. And so the epsilon ball centered at Y with radius delta is a subset of the epsilon ball centered at X with radius epsilon. All right. We'll now use this lemma to establish the metric topology. Again, let X with some metric D be a metric space. The collection script B consisting of epsilon balls, such that the point X is in the set X, and epsilon is some given number greater than 0, some non-negative or some non-zero number, non-zero positive number. This collection script B is a basis for a topology on the set X called the metric topology, induced by the metric D. All right, so we will show that this collection script B satisfies both conditions for the definition of a topology generated by a basis. So first, notice that the point X is in the epsilon ball centered at X with radius epsilon for any given choice of epsilon. So, for every point X in the space X, there exists at least one element B in the collection script B, such that the point X is in that element. So the first condition is satisfied. So next, let B sub 1 and B sub 2 be two elements in the collection script B. And suppose that the point Y is in the intersection of these two elements. Then, by the previous lemma, there exists positive numbers delta 1 and delta 2 such that the epsilon ball centered at Y with radius delta 1 is a subset of B sub 1, and the epsilon ball centered at the point Y with radius delta 2 is a subset of the element B sub 2. So let B sub 3 be the open ball centered at, or the epsilon ball centered at Y with radius delta, where delta is the smaller of the two values, delta 1 or delta 2. Then the point Y is in the element B sub 3, which is a subset of the intersection of B sub 1 and B sub 2. So the second condition for a topology generated by a basis is satisfied. And so the metric does induce a topology called the metric topology on the space X, where the open sets, the basis elements, are are epsilon balls for any given choice of epsilon, and for every point X in the space X. So we have that every metric space is a topological space. But the converse is not true. And another thing to note is that the epsilon balls are often called open balls, where the implied topology is the one induced by the metric D. Now I'm going to attempt to represent in a plane what this might look like. So let's say we have a point X and that we have an open ball centered on the point X, an open ball centered at X with radius epsilon. Then for any point Y, the distance from X to Y is the number d sub xy in the metric D. And so if we take the radius delta being the difference from epsilon and the distance from X to Y, we have an open ball centered at Y with radius delta that is contained in the open ball centered at X with radius epsilon. All right? So next we will show that the discrete metric induces the discrete topology. Let D be the discrete metric on the set X. Then D induces the discrete topology on the set X. Okay, so first notice that the open ball centered at the point X with radius epsilon. Well, let's choose radius 1 is the set of all points Y in the set X such that the distance under the discrete metric of between X and Y is less than 1. Now in the discrete metric, the distance is either 1 or 0, and so if the distance is less than 1, this means that we're looking at the set Y, set of all elements Y in the set X, such that the distance from X to Y is 0. And so this means that we are looking at those points that are exactly equal to X, and so we have the singleton set containing X. So every singleton set is open. Now the empty set is open, since the empty set is the intersection of two singleton sets containing the point X and the point Y respectively, where those points are distinct. And every non-empty subset of X is a union of some singleton sets so every non-empty subset of X is open, since unions of open sets are open. So, as every non-empty open set, non-empty subset of X is open, and the empty set is open, we have that every subset of X is open. Every subset of X is open. And that is the discrete topology on X. All right? So the discrete metric induces the discrete topology. So now new definition. Let the collection X with some topology tau be a topological space. The space X is said to be metrizable if there exists a metric D on X such that this metric D induces the topology tau. So the example we just looked at, the discrete topology is, or the discrete topological space is a metrizable space, since there exists the discrete topology on X that induces the discrete topology. So we'll be looking at some examples of metrizable topological spaces. But first note, or let me state, that metrizability is a topological property. That is, it is preserved. It is the condition of being metrizable is preserved by homeomorphisms. We will be looking at that in the next lecture, but I want to go ahead and state that now. All right. So new definition. Let X with some metric D be a metric space. A subset A of the underlying set X is bounded if there exists some number M, that is, some real number M, such that the distance from the point A sub 1 to A sub 2 is less than or equal to M for every set of points A sub 1 and A sub 2 in the set A. If the underlying set X itself is bounded, then we call the space a bounded metric space. So notice that boundedness is not a topological property because it does depend specifically on the metric that is used on the underlying set X.